surface analysis technique gives information of the material which are the less than 100 nanometer in the depth. So most of the time, all the XPS machine itself consists of AES and EELS. EELS also consists in your TM analysis also. So these are the attachment which are goes into that main machine. So how I am going to present it, I will give some brief background about XPS. Then I will start with the XPS instruments. How does this XPS technology work? There are some kind of other electrons also there. So how to understand those of things. Then there is a cylindrical mirror analyzer where the actual the analysis takes place. That's the analyzer. Then equation, kinetic energy versus binding energy, spectral background, how to interpret that, then identification of the peaks, and some of the examples I will explain so that you will get more uh, accessible to these kind of spectroscopy technique. So in broader terms or another way, this XPS is also known as electron spectroscopy for chemical analysis. So it investigates for the chemical composition at the surface. So what is and why it is used? XPS is typically used to identify the element or composition on the surface up to 1 to 12 nanometer. Of course, the X-ray can penetrate up to 100 nanometer, but we will get more useful information from the surface of thickness from 1 to 12 nanometer. It's also used to examine the contamination at the surface of any bulk sample. It's used for chemical state identification of the element in the sample. That's called chemical composition. It also find out the what is the binding energy of that particular electronic state of that material. And apart from that, we can also find out the thickness of the material. Say, I will give some oxides form on the surface. That also we can identify with this XPS technique. But before that, what kind of material, what kind of samples we require it, that also let's understand. XPS is generally or routinely used for inorganic compounds, metal, semiconductor, polymer, ceramic. However, sometimes polymer or organic materials are not, readily used because they can degrade with the X-ray energy source because there is a heat generation. So they start to degrade it. So organic compounds or organic material, it is not routinely used. So what kind of elements we can test or we can understand, we can get the information. So XPS detect all elements except which are greater than 3. It cannot detect hydrogen and helium because their diameter are much more smaller than to reduce or to that orbital is very much more small and that XPS cannot detect it because the X-ray source has that limitation. So what is XPS? Everyone know XPS. XPS is nothing but it's an old Einstein story. Einstein's idea of photoelectric effect, which is developed in 1905. And of course, Einstein got this because effect as a Nobel Prize in 1921. So what is it said? It's simply when it's a concept of photon, and that photon when bombard on any surface, okay, it eject an electron. Okay, so that ejection of electron is the concept upon the bombardment of a photon. So taking these concept during mid 1960, Dr. Kai Shenbach and his research team. Can you see here? There is a photograph of uh, the Kai Shenbach. He developed an instrument, okay, and to analyze this kind of technique. And in 1981, this Dr. Seinbach also awarded with the Nobel Prize in Physics for developing this XPS tool. So, since the name says XPS means X-ray, there are how to understand what is mean by X-ray. So, the X-ray for in 1895, German physicist William uh, Röntgen, he developed this first initially how the X-ray got generated, and he simply made without any doing patent, he made it. He gives his technique to entire world to use as an application for medical application. So he was very kind and generous to give this simply X-ray technique to the entire world. So the X-ray where in this XPS where we are using is starting from 0.01 nanometer to 10 nanometer. If you see, this is a diagram. In this area comes under X-ray. Now, this is a broad area. If you see, the its starting range from the photon energy from 100 eV to 1 mega million electron volt. Okay. So, is there only one material that generate X-ray? No, there are different materials where based on the application, we can use those kind of X-rays to generate the X-ray sources. So what are the materials? Tungsten, copper, aluminum, yttrium, zirconium, magnesium, silicon, titanium, and chromium. These are the target material from where we can get the X-ray source. So here, if you see the principle of generating the X-ray, it's and there is a on the beside of that there is a modern X-ray tubes. How the X-ray tubes which are right now compact, but initially it was very much big. So how it's works simply, X-ray comes here where there is one heating element is there, and in the ultra high vacuum 10 to power minus 6 tube, glass tube, that heating element is mostly tungsten. Okay, that generate the electron by applying little bit voltage. Since it's an under voltage, there is a target. Now here I can say target K alpha, alpha, beta. There are different kind of radiation spikes are also there. In terms of the tungsten, here is the tungsten target. Now this heating element generate the electron, a bunch of electron, and it was directed to fall on this target. Now this target is connected, it's called anode, and it is connected with a high electron volt around 20 ev or 10 ev depend upon the application, and from there the X-ray start generating. Now for the anode, when we are giving such a high voltage, it become very hot, and to control it we have to put a cooling material or cooling fan or cooling water. Now when there is a tungsten, if you see, there are spikes, these called characteristic radiation spikes. And these spikes are generally used to analyze in the any spectroscopy technique. So those are the K alpha 2, K beta 1, K alpha 1. So based on their energy, how much energy it is used. So regarding this XPS, this X-ray generally how it works. So it's radiate on the surface and hitting to the core electron of the atom. X-ray penetrate the sample in a depth in the order of some micron because it's an X-ray. Okay. So, however, we can get an useful information from the depth around 10 to 100 angstrom on the surface. So, typically for XPS technique, there are two kind of targets are used: magnesium K alpha and aluminum K alpha. Now, remember these magnesium K alpha and aluminum K alpha. Here, in the previous slide, I have shown these are the peak. Can you see K alpha, K alpha? So regarding the magnesium K alpha, we are going to use for the X-ray. It has a energy of 1253.6 electron volt. And for aluminum K alpha, photon having energy of 1486.6 electron volt. Now, these energies are normally used as a single energy source. Okay. And this is known as monoenergic X-ray source. Okay. Now, why Mg and aluminum only? We will come into that part later on. So, before that, one need to understand what is a core electron. Core electron is an electron near to the Fermi level. Okay. And is this far away? Core electron is near to your atom core. That's why core electron is called. So an electron very near to the Fermi level and far away from the nucleus moving in a different direction, that does not carry any information. Okay, that's why we are not considered about that electron. Okay, so what is Fermi level? Fermi level is the highest energy level occupied by an electron in a neutral at zero absolute zero temperature. And the binding energy is always calculated with reference to the Fermi level. So the core electron are very close to the nucleus. If you see this diagram, if this is an atom, near this dark blue line, there is a dark dot is given. That's a core electron, and outside there is a valence electron. Okay, and that gives particular information of about that element. That's a binding energy of that particular element. So the core electron have a higher probability of matching with the energy of aluminum K alpha and magnesium K alpha. So there comes why we selected aluminum K alpha line and magnesium K alpha line, because the core electron energy has a highly matching probability to match with all kind of materials or all kind of atoms. Okay. Now, if you see here, there are various states 1s, 2s, 2p, and those are defined in most of the time. If you see any XPS spectra, you will find 1s, 2s, 2p. So those are the shells around that atom. So what is the binding energy? That is important, because all we are going to play with the in the entire lecture we are going to listen binding energy, binding energy, binding energy. So what is that binding energy? Binding energy is the characteristics of that core electron of each element. So each element has a unique binding energy related to that core electron. So this binding energy is determined by the attraction of the electron to the nucleus. See, for example, if you take out an electron, or if we are taking an electron with an energy x which is pulled away from that nucleus, the attraction between the electron and the nucleus decreases. And as a result, what happened? There is a binding energy also decreases. Now that is the energy we are going to measure it. Eventually, there is a point where the electron is set to free in the nucleus, free from the nucleus. So that is the energy where there is an attraction between the nucleus, and when we pull out the energy from that, that bonding between the nucleus and the outer shell is called your binding energy. So in terms of the instrument, I will give brief broad how it looks like when you go anywhere. XPS moves more or less will look like this as an external part. So XPS, as again I told you, it's a ESCA. It is called an electron spectroscopy for chemical analysis, and it is widely used technique uh, because it's very simple and easy to use, and data is easily analyzed. So previously what happened, XPSP, there were very less instruments available, or there is a less facility available. That's why we are not able to find out, and we feel that it's very complex to interpret it. However, when there are many sources come, then we started feeling, yes, it is very useful and easily understand. So XPS again, it works by irradiating the atoms of the surface of any material with X-ray photon and causing there is a ejection of the electron. So some of the terminology I am repeating because these words are need to be understand very carefully. So this XPS is controlled by a computer system. Then the computer system will control this X-ray source, which type of X-ray we have to use it, and prepare the machine for analysis. So this is required. This is a chamber where you can see uh, pointer. Okay. This is a chamber. From here, the sample get inserted inside that, and we required ultra high vacuum environment. Why we require ultra high vacuum requirement? Why we require ultra high vacuum? Because there is a contamination. Since this is a surface sensitive technique, so any contamination is give result in a wrong way. So to remove that contamination from the surface, we require ultra high vacuum. So how much ultra high vacuum required? Typically vacuum required which is more than 10 to the power minus torr. Now this 10 to the power minus 9 torr vacuum is required to remove the contamination. Also, this XPS is also incorporated with some uh, argon gun also, argon ions also. That also used to remove the contamination from the surface by bombarding the argon ion. Okay. Similarly, sometimes there is a heat arrangement also given inside to the holder to remove the oxygen, which is as an contamination to the surface. Okay. So XPS, these modification or these contamination removal technique will damage a little bit sample surface, but those are very negligible because we want to take the information from the surface of less than 10 angstrom. So in a little zoom area, we can see this is the X-ray source. In a vertical, it's given. There is a this is ion source required to remove the contamination as well as to understand the surface of the to clean the surface from the contamination. There is a SIMS analyzer. As I said, there is another technique where we can also use XPS. So this is an add-on attachment to understand. And there is a this is a small area where we can introduce the sample to the chamber. So again, a little bit more focused area. The sample will be introduced through the chamber that contact where it contact with the first outside environment. So here is a first chamber where we can introduce the sample, and there is a second ultra high vacuum chamber. So initially, first we have to insert the sample, make it clear that the basic part its contamination is goes on, and then we introduce, because we cannot introduce directly at ultra high vacuum. So there is a one window is given where there is a less vacuum, and then we start to incorporate with a ultra high vacuum. So after the first chamber, which is at a low vacuum, the sample will be introduced into the second chamber. Why low vacuum? Because they require a special kind of pump which gives that kind of vacuum level. So there are, see, as in schematic, as in side view, we can see this is a from where the sample is inserted, and here is the holder. So when we introduce this, there are two type of pump used here. One is roughing pump and another is ion pump. And nowadays there is one more pump is used, that is a turbomolecular pump. So generally turbomolecular pump has a capacity to bring the entire chamber at ultra vacuum level. And there is a rough pump because without the basic volume, these turbomolecular pumps cannot operate it. That's why we have to connect first the roughing pump. It will bring the entire chamber at vacuum level of 10 to the power minus 3. And this is the minus 3 is the best pressure to start the ion pump or the turbomolecular pump. And once the vacuum come, then we bring that near that sample holder. So if you see another, there is a SIMS analyzer. That is also one technique to understand. There is an ion source to bombard on the surface to remove the contamination. And there is an X-ray source. There are the detector. This is the axial electron gun also is there. And look at this. These are the CMA. This is called cylindrical mirror analyzer. That is how actually look like. I will show in the next slide. So there are two slits. You understand the terminology. This is one slit and this is another slit. Okay, and there is a detector. This detector will help to detect those electron which are coming from the sample. So next. So in a short summary, I will bring back all to understand, recap those things. In the X-ray technology, we are using monoenergic X-ray beam to which is emitted, which is bombarded on the surface, and the photoelectron are emitted from the surface of the sample. Typically, two energies are used. There is aluminum K alpha that is having energy of 1486.6 electron volt, and magnesium K alpha having energy of 1253.6 electron volt. Now there is a this X-ray penetrate about certain micrometer. However, we will get more useful information from the surface of having 10 to 100 Armstrong of that particular sample surface. We require ultra high vacuum environment to eliminate the excessive surface contamination. And there is a cylindrical mirror analyzer which measure the kinetic energy of that emitted electron. That's why the cylindrical mirror analyzer is an important part of the X-ray system. So then there is a what? There is a spectrum plotted by the computer from where the electron is detected and which is got connected to the computer. Now the computer, what computer does, the binding energy can be determined by their peak position and the elements present in the sample identified. Okay. So these are the brief what we have just understand in the previous slide. Coming to the next, now how the it works. That's a crucial part. Now look at here, there is a sample I already shown as a brown line. And here, first of all, come your X-ray source. This is again a tube, X-ray tube, where there are two sources. Similarly, it's got connected with each other. That is magnesium source and aluminum source. Then this is an element which got heated up and which generate the bunch of electrons. Those bunch of electron were bombarded on the target, and those targets, see, these got heated up, and then after heating, we apply a high 20 kV of energy source, electron volt, apply voltage we applied, and 20 kV volt, when we applied it, those bombarded electron on the magnesium target, it started generating the X-rays. Now, when these much of we apply the voltage, it become very hot. That X-ray source become very hot. To control it, we have to supply a water. That's a cooling water. So whenever you see any X-ray source, there is a water source is always given to reduce the heat. Okay. Now again coming to the magnesium K alpha line, and second one is aluminum K alpha line. You know now the photon energy of 1486.6 electron volt for Mg, it's 1253.6 electron volt. But look at the down, that is called line width. So what is that line width? Means there is a measurement resolution. So this resolution define that how much resolve your sample. So what is the step size of your sample? So that define line width. Line width define your resolution of your uh, graph. Okay. So if we want more resolution than 0.7 or 0.8, we require a high energy source. But most of the time magnesium and aluminum use because it suffice all the activity. It control, it identify entire work, entire the elemental mapping. So that's why it's commonly used. Now, once the X-ray bombard on the sample, what happened? See, for the sample, it is very important to connect that sample to the ground. See, what happened in SEM or TM, there is a charging effect come. When you see that SEM TM lecture, you will say charging effect, charging effect. Here also, when we do not connect our sample, the sample get charged. And what is the effect of that sample charge? Once the sample get charged, your peak got shifted, binding energy shifted. So if the binding energy got shifted, your interpretation all goes wrong. So that's why we have to always connect the sample to the ground. So when you give sample for X-ray analysis, please do ask, have you grounded my sample? Otherwise, after interpretation, what will happen? Array, my peak got shifted. So what to do? Just you have to confirm that with the operator. So when we have connected, it get grounded. After that, what happened? This electron get ejected and it travel in a straight line. And when it travel, it it will disperse everywhere, okay, in the chamber. To make it in a straight line, we have to bring all these electron in a straight line by arranging those electron through passing through a lens. This is not a optical lens, this is an electromagnetic lens. So the all the scattered electron of punch coming from that sample, it get focused in a single line. Then what happened? That entered into a cylindrical mirror analyzer. What is this cylindrical mirror analyzer? This is again a plate, metal plate, okay? And there is a slit. Now this slit will define how much area of your interest need to be understand. If the smaller the slit width, means your smaller area is getting analyzed. If we increase the slit width, you will get more area to take out the electron. So this slit width is very important. Now these cylindrical mirror analyzer are connected with a different potential. The middle one is called positive potential and outer is called at negative potential. Now these electron coming from the sample are having different velocity. Now this voltage generally most of the XPS machines, this negative is kept at a constant. Okay, why it is kept constant? Because we want to find what kind of elements are available. Then we vary this positive voltage, and from that voltage we can understand what kind of electron and what kind of composition on the surface. So when the electron comes from that, some what happens, these electron have particular velocity. Higher the velocity, they get attracted to the negative side, okay, and the lower the velocity, and they got hit on the surface and they get grounded. The lower the velocity, what happened? It will hit to the positive side. But what happened, or particular that element or particular that atom, when the exact velocity come with that particular voltage, will get clean electron which is passed through the exit slit. Okay, and now what happened? This exit slit, there is a detector, and that detect the how many electron came from that cylindrical mirror analyzer. What happened? It count how many electrons are there, and that number of count is given to the computer system, and that plots your XPS data. Now this is a general mechanism inside what happened when we are doing in the XPS analysis. Okay, so if you see the particular velocity of electron only pass through that slit. Okay, other electron get bombarded with, and that is not the core electron, because core electron has a particular energy that comes out from that uh, sample. Okay, so when this phenomena occur, when X-ray hit on the sample, how the changes and how the core electron come into the picture. See, this is a say this is a surface of your sample, and this is the atomic layer. So first layer, second layer, three layer. Dark blue color are the atoms. Okay, on the whereas the light blue color are the surface. Now look at this. There are different color code I have given here. The purple color, if you see, this is a electron top layer. Okay, this is a electron coming from the top layer. Then the again dark purple is also given here. These are coming from lower layer of the electron. Then there is a red color is given, that is coming because X-ray is not only penetrating on the very up top surface. It goes up to some micrometer level, na? So micron level. So the electron also coming from the lower level. Okay. Then this black color are your X-ray sources, and if you see, this is the outer surface and the inner surface. Okay. Now what happened? The X-ray will penetrate to the core electron of that particular atom, and some electrons are going to be released without any problem, because those are on the surface now. So kinetic energy easily come out from that electron. Okay, giving the kinetic energy of characteristic of particular element, because that particular atom has a particular kinetic energy. So of that core electron. So it will come out. But what happened if some of the electron are coming from the inner layer? So what happened when they are coming from the inner layer? They are hit with each other. And what happened upon hitting with each other, their energy goes down. Okay, and that contribute to the noise. Okay, so how the noise get contributed? Before that, let's have a zoomed area of that. Okay, so in the zoom area, if you see here again X-ray source, and these are the outer layer. So these electrons are easily coming out, okay, without hitting with the other electrons. But what happened if it comes on the lower surface? These are the core electron, black dot, and those are hitting with each other, here hitting, here hitting. So as a result, what happened? There is an electron collision comes and it lower down the energy. And the lower the energy, your noise comes to the picture. So that noise is always increasing. So the collision cause a decrease in the energy of the electron, and it is no longer will be contribute to the characteristic of that particular element, because it's a noise now, so it's not the characteristic of the particular atom or the particular element. So that's called, we have learned that collision type, electrostatic collision, elastic collision, non-elastic collision. So here are that concept comes into picture. Okay, so the electron without the collision are more important to understand what is the core energy, core of that energy of that particular atom. So now the cylindrical mirror analyzer, the electron is ejected, will pass through the device called CMA. And the CMA has a two concentric metal, as I said, shown in that animation, okay, with a different voltage. One of the metal cylinder will have positive voltage, which I have shown at the center, and which is other will have a zero voltage. This will create an electric field between those two cylinders, and those electric field will exactly pass the right velocity of electron, which will come out from that outer slit. The voltage on an CMA for XPS and other electrons are different. Now, sometimes what happen? These XPS is also attached with an other electron spectroscopy. Okay, so the settings for the CMA are different for XPS and other electron spectroscopy. So that will define and that will give different result. So what we'll do when an electron pass through a metal cylinder, they will collide with one of the cylinder, or they will just pass. Okay. If the electron velocity is too high, it will collide with the outer. That's what I said. If it's go too slow, it will collide with the inner. But the only electron with the right velocity will pass through the cylinder and reach to the detector. So the voltage, so the change in the cylindrical voltage, the acceptable kinetic energy will also change. So we can have an entire scan on the sample to get the kinetic energy of that particular, from that particular. See, if you have multiple composition of your sample, then it will scan entire energy range. Okay, and then you will get this material contain this element, because the scan will give the peak related to particular that element. So this is a simple equation. Of course, if it looks like a simple, but when it become more complicated, when we have to find it. So kinetic energy is measured is equal to your h mu. H mu is your photon energy of that X-ray source, which we can control it, binding energy, and their work function. Now this work function is calculated very precisely, and after the calibration only we'll get to know that this is the work function of your material. Kinetic energy, which is measured from the X-ray XPS spectrometer. Binding energy, we have to find it out, so that's an unknown variable. Okay, so if we know the h mu kinetic energy work function, we can easily know what is the binding energy. So the equation will calculate energy needed to get an electron out from the surface of a solid. By knowing the Ke, nantar photon energy work function is binding energy can easily calculated. Now, in previously, I have shown that the noise, how that noise can created. And if you have any plot of XPS, it will look like the same. Okay, how it will look like? The kinetic energy can be plotted depending upon their binding energy. Okay, so here is your binding energy, and here is your number of electron that is detected or counted by the detector. Each peak represent the electron of that particular energy and the characteristic of the particular element. Okay, so how that, so if you see the graph, binding energy will always increase from right to left. So this is right to left. So binding energy. Whereas if you got the plot where you can find out my energy is increasing from left to right, you have to understand the x-axis is not the binding energy, it is the kinetic energy. So always look at that. Binding energy, it is always start increasing from right to left, right to left. So increasing. So your XPS graph also will always on a higher side, increasing side. Okay. These are the convention and tricks where you can understand, this is a plot of binding energy or the kinetic energy. I will show some of the example also. So while interpreting these X-ray spectra, you have to always understand X-ray will hit the electron in the inner bulk of the sample, and the electron will collide with each other, and that will reduce the energy and that will create the noise. Okay, so these all noise are summation. That's why it is always rising, because this noise is added in this noise is added in the next. So that is a sum of noise. So a noise totally, that's why your plot is always on a rising side from right to left. So what is the XPS spectrum? How we can understand the XPS? So XPS peaks are very sharp. Okay, when you have any graph of XPS, you will always find there are sharp peaks. Some peaks, some of the electron are other electron also, which come out from during the measurement. But how to understand? The other electron are not sharp. Their peaks are very brighter. Broad peaks are there. So you have to understand that's not my area of interest because that's an other electron. Okay. Then to show an example, I will show one of the aluminum foil typical example. Look at this. Here, the graph is your binding energy. Source is used as a magnesium source, and this is always rising side. So what it gives, this is number of electron here collected, and here your all kind of elements what are observed in the aluminum foil. So in the aluminum foil, what you can see, there is oxygen is also there, aluminum peaks are also there, carbon peak is also there, oxygen 1 is there. See, this is the auger, this is blunt. You can say this is not the your binding energy of that. This is the auger electron. If you see, this is the same kinetic energy. It is rising from left to right. So we look at this same graph. The kinetic energy is rising. Okay. So this is called an Auger spectrum, where we can also get some information from that. But here we are considering only a XPS. Okay. So how to identify those peaks? Check the peak positions. You have any XPS plot? First of all, check your peak positions. 1, 2, 3, 4. How many peaks are there? You have to identify those peaks. Okay. Then what happened? There are photo emission lines, other lines of that particular element that you have to eliminate. But what happened? Most of the time you can also see there is a spin orbital splitting. What is mean by spin orbital splitting? Spin orbital means same the material, there is a splitting of the energy. Okay, orbitals are getting splitted. Okay, so what are those? Those are generally PDF peaks. The orbitals, PDF orbitals are most of the time, most of them, those are only observed as an split orbital splitting only. How to identify? We have to take a ratio. That ratio will define how much spin orbital, and those are constant. Those are the one of the interpretation skill to understand and confirm that your what material is that. So if you see for PDF peak only, we can observe this kind of orbital. Okay, so look at this one sample. This is a gold sample, gold film, where we can see two peak, 4d5 by 2 and 3d5 by 3 by 2. Okay, so the spectral separation between the two peaks are named as a spin orbital splitting. There is a separation, but that belongs to gold only. Huh? The value of the value of the spin orbital splitting of the core electron of an element in a different compound are nearly same. So if you have one gold compound or any say tin oxide compound is there, tin oxide or tin compound in one compound, or someone already made some tin with a different composition, but all tin having same orbitals value, splitting orbital value. Okay, so it's an one thumb rule to understand what kind of material is there. So again, one more, if you see the peak area ratio, the ratio between these area, one area and two area under the peak, that is also same in all the, say example is a gold. Gold, all the peak ratio, peak area ratio of that spin orbital will always remain. So for P, it is 1:2. For D, if you say 3 by 2, 5 by 2, then the F 5 by 2, 7 by 2, the area ratio will remain same. So we can always conclude from that interpretation that the spin orbital splitting and the peak area ratio help us to identify the elemental identification. What kind of element is there? So these are the peak notations. Some azimuthal number, electron number, those are we have already seen. And notation, if you see, always you will find in XPS they say 2p 3 by 2, where this is n number, L is azimuthal number, J is your coupling. So J is equal to L plus minus S. S is your spin orbital, which is always positive or negative. So S may be plus half or S may be minus half. So based on that, if we can find azimuthal number P 1 by 2. So if P 1 by 2 is there, 1 by 2, 3 by 2, you have when the ratio under area ratio under the two peak, if you see, it always 1:2. Okay. So 1:2 comes, you have to understand it is a P by, it's a P orbital. Okay. If you see D orbital, there is an area ratio always 2 by 3. If there is a F orbital, you will find the area ratio of 3 by 4. So those are the notations we see generally during the X-space interpretation. So identification of this peak, once you identify the peak, these are particularly characteristic peak of that particular element. We have to find, we have to assign those from the standard fingerprinting technique. So there is a standard database. For, you know, for XRD also there is a standard JCPDS database. Here also you will find a standard database. So from that database, which is already assigned binding energy of particular element, we have to understand what kind of binding energy related to what material. So once the spectrum is plotted, you can look the designated value of peak energy and the plot the graph and find the element present on the surface. So this is a fingerprinting technique. Understand how it works, how we can measure. So where you will get standard database, that also I will show in the upcoming time. So as I said, contamination that also have some effect to shift the peak. Okay. Also, sometimes what happened, there is a chemical effect is also observed. Now, this chemical shift also we have to take consider. How to consider the change in the binding energy of an core electron of an element due to the change in the chemical bonding of that element. How the change in the chemical bonding occur? There is an electrostatic interaction between its and its nucleus, and it's get reduced. See, this electrostatic shielding of a nuclear charge from all other electron in the atom, including valence electron. So these are the complex terms. But in a simple language, when there is a withdrawal of an valence electron, that is called oxidation, your binding energy also increases. So when you see your peak got little bit shifted, you have to understand that there is a oxidation occur. Okay, and what happened when there is a addition of valence electron charges, there is a decreasing binding energy. So it's an chemical shift. While considering or while matching this binding energy with the standard data, if peak got shifted, you have that interpretation. Yes, there is a withdrawal of an electron charge. Then oxidation, surface got oxidized. So that's why little bit peak is observed. So just take an example of how that shift occur. So this is a typical TI sample, titanium oxide sample, and TI sample. How this peak got shifted. So TI has a 2p 1 by 2 and 2p 3 by 2. Okay. If you look at this TI and TI 4 plus. Okay. TI and TI 4 plus. There is a charge withdrawal from Ti to Ti 4 plus. So the 2p orbital get relaxed to the higher binding energy. How we can see that? Ti 453.8 electron volt is the binding energy, where in TiO2 what we get is 458.5 as an binding energy. So there is a shift which occur when there is a oxidation. But one needs to understand the spin orbital splitting. It always remains same. 5.7, 5.7. So the spin orbital is always constant. So that is an confirmative state, confirmative test. You can say that this is a TI sample because spin orbital splitting not shifted. Area under the curve also is not going to shift. So the chemical shift information is very useful tool for the functional group or the chemical environment or the oxidation state to understand that. So you have to understand if any surface got oxidized, there is a small chemical shift is also observed, but the spin orbital splitting will remain same. So how that shift is useful, that is useful to identify the thickness of an oxide layer. So take the same example of your aluminum. Aluminum, how it will measure? So XPS generally measure the thickness which is less than 9 nanometer, and most of the time these oxide layer are very thin, less than nanometers. So usually the binding energy of the oxide and the metallic species are separated by a few electron volt. Thus, a oxide is very thin, less than 9 nanometer. So it is possible to distinguish the contribution of both oxide and metal uh, photoelectron. So take an example. Okay, for the aluminum, it easily get oxidized. And how to understand its thickness? There is a simple formula. This is a universal formula for that. D is the thickness in nanometer is equal to 2.8 ln of in bracket 1.4 IO upon IM bracket complete plus 1. If you put IO and IM value, you will get the thickness of that particular oxide layer. So what is IO and IM? IO and IM are the intensities from the graph. You will get it now. What is the area ratio? What is the area? You have to put that area intensity under the curve. Okay, area under the curve you can find out of particular that. So IO is an IM. This is oxide area under the curve, and this is metal area under the curve. Okay, and when we put this value, see these are the aluminum metal and this is aluminum oxide. Okay, area under the curve we have to put in that equation, and in you will get what is the oxide thickness. Here in this case the oxide thickness is 3.7 nanometer. So that also we can easily identify. Now this is an complementary technique to understand what are the composition of your material. See, you are making a different nanocomposites or different material you add it. But how to validate? There is a EDAX we can typically use, XRD we use, but in terms of quantification, EDAX, ILS, or the XPS are typically used to understand. If you don't have the ILS technique, but you have the XPS, you can quantify or verify with your EDAX data how there are different ratio or the what is the composition is available. So sorry. So take one example, how to identify what are different composition. This is a iron sample which has a different contamination, like manganese is also there. Contamination in the means this is a composition. So iron is made up of magnesium, calcium, then sodium and nitrate. First, what is that? You have to identify your element. Say oxygen, Fe, then calcium is, nitrogen is there. Then you have oxygen loss, magnesium, Fe. So first of all, identify. Then what you have to do, identify and find the area under the curve. Now this is the equation where Cx. See how to find the percentage, this formula is used. I will tell in the next slide what is Ix, Six. Okay. So first of all, find the area under the each curve. How to find the area, that's number, na? That is a separate software. I will explain that part also during the upcoming slide. So look at this. This is a table, a standard table where we can have the atomic sensitivity factor. You can say as a correction factor for of each element. Okay. So look at this carbon. Carbon having 0.205, like Fe is having 1. So you have to first, this is standard data available. Okay. So you have to take this table while measuring the calculating the composition. Okay. Now, when you summarize entire the things, you will find peak, their intensity. That is intensity here. We have to write down the area of that particular pK. Okay. So for the example, carbon having intensity, I mean the area is around 40,396. Oxygen having area of 27,286. Nitrogen 1s having area of 1,359. From where, if you see, these numbers are varying because you will get those numbers. See, carbon having a broader peak, so the area is big. Like sodium, magnesium have a small peak, that's why area is less. So right, like that, you have to first tabulate it. Then your sensitivity factor. In the previous slide, you have seen these are the sensitivity factor. Carbon having 0.205 sensitivity factor. Okay, so just tabulate those sensitivity factor. Now, what is that? I upon S. Our I upon S is the total summation of the I upon S here. This is a sensitivity factor and this is a intensity factor. So I define as a intensity area and sensitivity is defined as a S. So just do the ratio of both. Okay. So you will get this value. And from that, you have what you have to do? You have to do summation, entire summation, and put this value in the equation. Okay. So concentration is equal to, see, concentration is equal to Rxsx. So for example, if you want to find the carbon, you have this ratio divided by summation of this ratio. So what you will get, this total surface having 79.1% of your carbon composition. Carbon is available on that much surface. Then on the surface, how much oxygen? 17.39 percentage, nitrate 1.44%, your iron is there 0.52%, calcium 1.07%, Mn 0.49%. So you can verify this data with your EDAX data, okay? Or you can directly says that these are the composition which are available on the surface. Now coming to the example. So how the interpretation of XPS is how you more often do XPS, you will get more idea and more information from that. Just take two different kind of example. Now, one of the example here I have to show is one uh, composition is there where there is a organic, there is a polymer is there is a functional material is silver is added in that, and there are some glass is also there. So with a particular ratio. So for example, you take this is a silver glass 4, where the ratio of polymer is around percentage of polymer is around 70%. And here, if you see, there is a glass, the organic to inorganic ratio is around 42 as to 58. If you take glass silver composition with a high solid content with organic to inorganic ratio, where the 28% is your organic and 72% is your inorganic, that is silver composition. So we will take two distinct composition to understand how the XPS will measure the surface, analysis the surface. So, first of all, we know that what is a polymer composition. Polymer is simply a long chain of different uh, functional group is attached for their functionality. There is this aqueous developer group is COH termination is there. Then here is a cross-linking double bond acrylic group is added to have cross-linking agent, which help to give reactivity as well as adhesion. This group is added for flexibility, and this group is added, epoxy group is added to have heat resistance. So we have idea about this polymer system. So how to understand this polymer system? By taking FTIR, TG, viscosity. So once we optimize this polymer as a binder, we go for XPS analysis. What we do? We generally take this composition and print on a substrate. Okay. And understand, we take a broad spectrum. So here three cases are observed. One case is that the sample is ideal condition as printed. Second stage is the sample is exposed to ultraviolet light, because these are the special polymer which get cross-linked upon exposure. So photoinitiator is added to activate those kind of chain system. So one is unexposed sample, second one is exposed sample to see the how the chemical changes occur during this and how to understand these chemical changes. The XPS is the best tool to understand what is happening on the surface. Okay. And third one is the same sample we just sintered at 850 degrees Celsius, so that the all the organic part burns off and surface remain with some silver. Okay. To understand what is happening, we have taken three distinct cases. Okay. So look at these two samples. When glass and silver 4 number sample, where you have the more organic polymer system, and uh, glass silver composition where the organic is very less percentage. If you see both the cases, you will get same binding energy of 284.5 electron volt, that is linked to the carbon carbon or carbon hydrogen group. 288.6 binding energy is related to COH termination. 286.6 binding energy again related to CH2 or CH2CH3 linked to carboxylic group or phenolic group. Now you will have question, are from where you got this number? No, there is a standard database is available. That part I will show at the end of the presentation. Okay, so here what happened? This is an unexposed sample where what we have 1, 2, 3 peaks observed, and which are the and those peak are at particular binding energy. When we go to the next, the same sample when we expose to the light, the surface got changed. The unsaturated group becomes saturated. In the previous slide, here what we had double bond cross linked. Okay, so what we observed here, there is a one more additional peak came into the picture. Here, the peak is more prominent because organic content is more. Here is less prominent because organic content is less, but it shows that particular peak. How to understand? If you fold this graph at the center of the peak, there is a asymmetry. And where there is a asymmetry, you have to understand there is the another functional group which is connected, which is observed in the my surface of that particular sample. Here, what we observe, here is the asymmetry what we observe. That asymmetry belongs to carbon and aluminum binding energy that related to 282.6 electron volt. Similarly, here also we observe aluminum 282.6 electron volt. Otherwise, 286.6 and 288.6 is the constant. They don't change. But what we observe, there is a saturation occurs at the surface, and there is a new binding energy occur, which related to CAl bonding here also. This is related to carbon. Okay. When we go for oxygen, similar phenomena we have to observe, because the surface, there is a change at the surface related to your polymeric change. So unsaturation to saturation takes place with the carbon only. So carbon and the oxygen. So here the unexposed sample, we got two binding energies. One is related to 532.6 electron volt, and second one is related to 531.9 electron volt, which is related to CO bonding, because these are the unexposed sample. When we expose it, look at this. The entire peak got changed. What we observe, there are two different peaks are coming. That is related to 530 electron volt and 533. And that we identify that those are the oxygen related to carbon and aluminum, and here oxygen related to Al2O3 that is coming from the surface. Okay, so both the exposed sample also similar behavior. When we see the same unexposed or the exposed sample for the silver, okay, because that is one of the functional material, what observed, the entire polymer got encapsulated. Okay, the silver got encapsulated with the polymer system, and because of that silver we didn't get any binding energy. Okay, so that is the important conclusion what we observed from the entire film. But the same film, when we fired both the film at sintered at 850 degrees Celsius, what happened? The all the organic goes on burning or go all burned out and remain metallic silver, which has a binding energy of 367.9. There is a oxide because we sintered at air atmosphere. So 367.2, that is a silver oxide. There is one more bonding what we observed is that AlAg2, that is related to its binding with the substrate of Al2O3. Okay. So same case observed for both the sample, both the composition with higher polymer content and with a lower polymer content also. So we just tabulate everything what we observe in a different to understand what are the changes occur in both the cases. 286.6 everywhere is there, only there is a fired sample we cannot see because all the organic part burns out when we sintered it. 288.6 similar phenomena observed, but at 282.6 unexposed sample we don't have this carbon-carbon linked sample. We have the sample, we got a new peak that is linked to carbon aluminum. That's what. So like that, you can assign the binding energy from the what you got the data from the XPS graph. Okay. Another case now, everyone knows that the sensors are most of the time the sensors uh, function because that's a chemical thing, changes occur at the surface. Okay, all the sensors, surface of your material is very important. Here also, we are doing understanding how the sensor work, how to understand the surface of a sensor material with the XPS technique. Okay, so here three cases we observe. Okay, this is a lanthanum ferrite material. Okay, one is a spherical particle, another one is a fiber or rod kind of particle, and third one is that mix of both this composition. Okay. Now, what we observed during the sensing performance, since this is the oxygen sensor generally work at a high temperature, around 550 degrees Celsius or 66 100 degrees Celsius. So what is actually happening when the oxygens come at the surface of that particular sensor? So we consider three cases, and what we observe during the gas sensing measurement, this mixed sample shows more sensitive. Generally, it is known that the rod will give more sensing performance because it has a more surface area than your spherical particle. But here, when we mix it, we got this mixed sample having more sensitive. But we don't know why this has happened. How we understand that? We got the base resistance of all these. Powder having base resistance of 120 ohm at 600 degrees Celsius or 550 degrees Celsius. Fiber we got 2700 ohm, and for the mixture we got 290. Okay, so these are the base resistance. We connect with a multimeter and we see the how much resistance observed at 550 degrees Celsius or 650 degrees Celsius, you can say. And then we did XPS analysis of that sample. And what we observed, we take a oxygen and the Fe, because oxygen and Fe are the main culprit for sensing a mechanism. They changes accordingly in any sensor material. So oxygen mostly available in two form. Okay, one is a lattice oxygen and the surface oxygen, and we are much more interested with the surface oxygen. But how to understand? Here are the cases. A, B, C. Three cases we are saying. Again, A, B, C are the what? They are the three conditions: powder, mixture, and the rod. Okay. Here, what we observe that the ratio of oxygen surface to the oxygen lattice is much more higher than what we got is a single rod of lanthanum ferrite or a single small nanoparticle of lanthanum ferrite. That is one clue what we have got it. Another clue what we observed is that spin orbital splitting, or one here look at this spin orbital splitting. Fe, we have Fe2p orbital, na? There is spin orbital. So Fe2p 1 by 2 and Fe 2p 3 by 2. We got a constant delta E, that is 13.3 electron volt. So that confirmed that it is a Fe binding energy. Now for sensing mechanism, when there is a Fe comes into the picture, there is a change when there is an interaction with the oxygen. So it get Fe4 plus to Fe3 plus, and again Fe3 plus to Fe4. There is a transition between the Fe. Now these conditions we have taken at 650 degrees Celsius immediately. Okay, the same sample after measurement. Okay, so what happened? This why here 0 hour mentioned, that I will show in the next slide also. Look at the changes here. Fe4 plus Fe3 plus ratio. For the mixed sample, what we got is 1.06. And for the oxygen also, highest number what we observed is for mixed samples. So that confirm that our electrical measurements are correct, what we have done. Okay, so this is a confirmative test for my oxygen sensor measurement, that what we have concluded for the electronic measurement or sensing measurement is correct. Similarly, the same sample, we want to see how much changes occur when the same sample is exposed to 100 hours. You know, these oxygen sensors are typically used in automotive sectors where the exhaust come, or in a gas turbine where there is a high temperature and oxygen to fuel ratio we have to measure. So we have to see how much changes occur at the surface when we uh, heated, or when we sense this for 100 hours at 650 degrees Celsius. What observed? The changes are similar, or you can say the trend is similar. For the mixed sample, we got the highest ratio of Fe4 to Fe3 ratio. Oxygen lattice also what we got is a higher side. So we can confirmly say that the sensor will work up to 100 hours. So long-term study of that sensor also we can perform, or we can analyze that. So what is there? What are the applications? So as a summary point of view, we can see that how this XPS technology is summarized. To consider XPS is a non-destructive because very small soft X-ray is used and induced on the surface, and it doesn't destruct your sample surface. Okay. Second, it provides the information of the surface or the thin layer of your structure. And where are the applications? You can see the application in the industry, in the where is a polymer chemistry is there, polymer industry is there. If there is a catalyst, we can use XPS to understand what phenomena, corrosion phenomena, adhesion. We have to find the adhesion of your film. Then semiconductor industry is routinely used, dielectric measurement, insulating material, electronic packaging industry, then magnetic media, thin film coating, sensors. So XPS tool is widely used in the industry of these kind of fields. Okay. So good thing is that we have in CMET Pune, we have this XPS tool, which recently 1 year ago we got that this machine. That is a brand of 5 Genesis, which is the latest in the Pune right now. In we can, if you have some samples, you can easily send us. We can definitely do interpretation. Okay. So that's all from the uh, theory part of your XPS analysis. So if you are not tired, then I will have some demonstration how to do interpretation of the sample using the softwares. Okay. Hello, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
आता पुढचं जरा थोडं इंटरप्रिटेशनचं सॉफ्टवेअरचं सांगायचं आहे.
ठीक आहे
तर
सर, काय अडचण नाही.
ते मी सांगू?
Yes,
तेवढा
yes.
वेळ आहे ना अजून?
Participants are requested
ओके सर.
to share their views in chat box. Okay. सर कंटिन्यू करू शकतात.
ओके. Okay, I will have to stop this. And now I will show entire screen share. So as I said, this is fingerprinting technique where you will get all those data. So I have given two standard database site. Okay, one is your NIST, that is a National Institute of Standard and Technology. This also gives you a standard database, elemental composition, and their binding energy, so that now you can easily identify what kind of binding energy of element observed in of your material. Second one is lasurface.com. This is also a standard database site where you have different database related to XPS, AES, UPS reported. So if you see the XPS you will find energy or the element, chemical bond, spectra. So these are the database. If you go the element, you will find XPS. So here you can see. Now I want to see what is the element. Okay. So for example, I will find carbon because carbon is well known. Carbon search. So here you will get carbon. Carbon, what is their binding energy? If it is C1s, the chemical bonding with which? This is a graphitic carbon. If you got the binding energy of 277.1, you have to understand that it is related to graphitic carbon. Okay. Similarly, 283.93, this is CH bonding. So if you see the presentation, in the presentation I have assigned some of the binding energy. From where I got this binding energy? I got this binding energy from this database. That is CH bonding. Similarly, if you scan entirely, there is a much more database. You can easily find CO bonding, then the simply carbon oxygen bonding. So you can easily identify what kind of bonding or what kind of chemical composition is observed on the surface. One more thing, while interpretation, you have to do it. Now, this is related to carbon. I will show you some of the different also. So in different, let's see, I have Ti. Here you can see 2p, 2p 3 by 2, 5 by 2. So you have to find out which first you have to find out. So look at this. Titanium, Ti has a binding energy of 588, 558.4. Okay, this is related to TiO2. Okay, so TiO2. If you want to see pure Ti, there is a pure Ti peak also you can also find out. See, TiAl, nitrate oxide, TiN, titanium nitride, pure Ti. So you can have that particular binding energy. Now, this is related to TiO2, oxide film with Ti and Zr alloy. If there is a alloy, you can find out this kind of. So all here you can find out the all element and their particular binding energy. Hello,
Yes, sir.
sir, can
Yes,
you
sir.
see this side now?
Yes, sir.
Okay, fine. So this is one. Another area, another thing is that you want to know bonding between two carbon or different bonding. So here also you can found the chemical bond. Chemical bonding also you can see XPS. Now here I want to see carbon and oxygen bonding typically. Okay, so I will select here carbon. There is a carbon AB, carbon 1s, carbon cobalt CE, CD. It will come here somewhere. Share entire screen. Share. So here I will see carbon and here I will see oxygen. Oxygen. Oh, and search it. Look at here. You got the all database related to carbon and oxygen. Here again you can see the carbon. Carbon is always starting binding energy in the range of 281 to the end is to, let me arrange it as in binding energy. 288, starting from 288 to 292. This is related to entire carbon binding energy rate, related to all kind of carbon oxygen bonding. So you can identify what functional group is there and what the surface. Similarly, you can find out Ti or copper, you can say. can say copper. Cu. Copper. Copper also have different spin orbital. Okay, so copper 2p I am taking, and here again I am saying oxygen. Such. Look at it. Carbon and oxygen having only three kind of binding energy related to carbon and carbon. Which carbon is copper? Sorry, copper 2p 1 by 2. Okay, this is related to copper to Cu2O and CuO, and there is a reference also. And one copper is also interacted with the yttrium or barium. So that is also you can identify. These are the compound available in my composition. So this is one technique where you can plot the data. Now you got the database. Now you have to use software. There is a freeware software available. It's called XPS Peak. Okay. So this is an XPS Peak software. So what you have to do? You have to open your data. You have to import the data from the ASCII file. Okay. Now here, let me see the data I have shared on the desktop. So desktop. C colon. Here, HP. I will show you here. Here there is a database. Okay. Here take one example. This is database in the notepad. Okay. I will just submit personal. See my database path. Desktop, submit personal, desktop, and there. Okay. So let me see. C colon user. Text public document nine. Desktop. Difficult to find my desktop. File just try system data. Okay. Just a moment, huh? Let me find out. Or what I will do, I will copy this data in a different folder. Very simple. Control C. I will save this in the D drive, paste it. Okay. Now I'll open this. Open the software. XPS Peak software and D drive example one. So here is the data in the notepad. Okay. What I will do, I will open one sample, which is unexposed sample. AG carbon unexposed. Okay. Open. Okay, there is a problem reading the data. No problem. I will open the XPS file. So you have to open the node file here and then rewrite example final, and there is a XPS file. I want to show expose sample. Expose open. You will get this kind of structure. Okay. When and here also what happens sometimes, your the carbon correction need to be done. That is what I wanted to show. But again, let me try one more time. Open the ASCII file. ASCII file, and let me open this one step back. Notepad data. Origin. This is origin file. Sir. नाही असं नाही सर. ते मध्ये एक बँड असेल. मी सांगू सर. त्याला सांगून टाकतो. हो सर, हो सर. सीटिंगचं बघ कसं ते. सो याच्यामध्ये unexposed exposed notepad file open, reading the data. Import ASCII इथे बरोबर आहे. No, I will let you know that it's not it's not that much difficult. Somehow that path got changed, but I will show how to do that with the XPS. These are the XPS file where we have shown the sample of unexposed sample. Okay, now look at here. Here there are different peaks. This is related to your unexposed sample. And when I open exposed sample, GS7 exposed sample, you will get peak difference. This is related to oxygen. Okay, I just want to show carbon related to exposed sample. So now it's very easy to compare. Look at here. Now, what happened during the XPS measurement? Carbon need to be corrected. Now, all the recent machine, the user particularly give carbon corrected. But sometime what happened? You get a uncorrected data. How to identify carbon corrected data and non-corrected data? You have to see first carbon peak. If it is 284.6, then it is a carbon corrected. If it is away from the 284.6 anywhere, the main peak, then you have to see, you have to correct the carbon. Correct the carbon how much? So if it is 284 285, you can say, then you have to reduce it. How much? 284.6.4 electron volt. So when we subtract the 0.4 electron volt, you will get a 284.6, which is a carbon corrected. Now that 0.4 electron volt, you have to subtract from entire element. Okay, you have a composition containing different element. Then if it is carbon corrected with a 0.4 electron volt, you have to correct it with all the respective element related to that particular graph. Okay, then it is a carbon corrected. Otherwise, what happened? You will start matching with the standard database, and you will find, array, there is a peak shift in the entire spectrum. And what is the reason for shifting that peak? One reason is that your carbon corrected. It is not done. So you have to carbon correct it. Then how to use this software? First of all, you have to bring the background. Okay, here there is a background. When you open the peak, you will find similarly. For the carbon, you will get the range of 287 point, or you can change that also. Now here the background is given in this range because I have seen the area. I have seen the area here there is a much more asymmetry is there. Okay, then what I have to do, I have to use different type of fittings. Most of the time, surely or linear kind of fitting is used for XPS. Okay, so we have to put, we have to see this is a reference line with the fitting, and then we have to add the peak. Now, how to add the peak? One is, the standard reference from the database. This peak belongs to my which binding energy, because based on the asymmetry. Okay, so find out, this is the 284.6 electron volt. Okay, this is second peak is 282.3 electron volt. Another asymmetry is observed at around this is related to 286.7, and here is small, then one more peak observed is related to 289.05. So tabulate this peak and add the peak. If you see add the peak, a peak is observed here, got added. Now what I will do, depending on my orbital, I will select what kind of peak. Since carbon is a s orbital, I will select s only. Now there is a peak position. One need to understand, here you will get the area under the curve. Huh? So all the peak you will get area under the curve. Now here what you have to do, this always you have to remember that full width half maximum of that peak, na, it should be always less than 2 and more than 0.5. Okay, then you have to see my fitting is exactly matched. Okay, and then what you have to do, optimize the peak. Now already this graph is optimized, the addition of one more peak will do nothing. I will show, I will say optimize. What happened, optimized peak? The all peak gone, because it is exactly matching with those 4 peaks. And how do I got to know that? Look at the blue color and the black color. When the blue and the black color exactly overlapping with each other, you have to understand my fitting, or you can say in the XPS language, it's called deconvolution. Okay, so it got deconvoluted, and this shows how many compounds are available in the polymer structure, this organic structure. 1, 2, 3, 4 peaks are there. Okay, so how to understand it's got fitted? Look at this value. This summation value should be very near to your zero value. If it is got, you have to do optimize all, much more optimize. See, look at the value. This number got changed, and it is tending toward the nearest to 1 or 0. And how it goes near to, the peak got more fitted and fitted on the, that black line is got fitted exactly with that blue line. Okay, so you can say this is a deconvoluted peak of my sample, and this deconvoluted peak help to interpret how much, uh, in the example I have shown, na, Fe3 plus Fe4 plus, you can easily identify Fe3 plus ions are more or Fe4 plus ions are more. And based on those ratio, you can identify what chemical changes occur at the surface in your sample. Okay, this is how it is used. Okay, for the interpretation. Similarly, when I see the same sample for oxygen also, oxygen, you can see exposed sample. Okay, here also see oxygen, you will get a binding energy of around 536 to 528. Here, what I observed, there is a broad peak, but when I start to overlap or fold it at the center, I will see there is a asymmetry here, asymmetry is here. So asymmetry means there is one functional group or there is another element which is getting binded with that compound which has a specific binding energy. So here also I fitted with 1, 2, 3 and did optimized all. When I do optimize, the blue line and black line are mostly overlapping with each other. That indicate that now it got fixed. Now this is a sample of exposed sample. Okay. When I see the aluminum, let me see, let me show that also. Uh, let me see different uh, sample also. Example 1, example 2, let me see NiP2 nickel sample. let me show. See, this is a nickel. Okay, nickel sample. I don't know which sample is that, but this is nickel sample within our lab, and we want to show how the XPS got changed. How what are the functional group? So here we found there is a one, another one, and this one. Three peaks are there related to nickel. Okay, and in the same sample, if we see sulfur, open it, sulfur got two peaks. Asymmetry means that sulfur is definitely bonding with the nickel or tin. Okay, so this is one more SN tin we have used. In the tin also we got, look at these two distinct peak of tin. So what these say? These are the nickel peak with a spin orbital splitting. Exactly. The binding energy between these two will remain as, and the surface area ratio, that orbital area ratio, na, it will be exactly matching with that one of the 2p or 2p 3 by 2 5 by 2 or SPDF any orbital. So these are how we can do interpretation. See, interpretation is that might, until unless you plot it, you cannot interpretation do it. So plotting is one of the critical part, and there is a software typically used for the plotting or deconvoluting this XPS peak. There are numerous softwares are also available, but XPS peak is more simple to understand it. Okay, so this is another part of interpret how to interpret this XPS from the raw data and plot it and calculate the area ratio. Now this area ratio, no, you can easily find out area under the curve. Huh? That is what also I wanted to show, how to identify the area under the curve. Na? You can see here. See, now this peak and this peak. If I selected one peak number one, I got the area under the curve is around 16, 1,60,029 is the area under the curve. Okay. So while finding the composition, na, you will require this area under the curve. Na? So how, from where you can get it? You can get it here. If I selected on second peak, I will get the area under the curve like 98,215. Okay. So look at this full width half maxima. Full width half maxima is 1.3. Under that 2. See peak position. Now I know, confirm that this peak belongs to my this functional group from the database. I can fix it by making here fix p. Now this is a p orbital. That's why I have selected p orbital. Okay. So these are the peak. You can add the peak. You can delete the peak. You can read all the peak. And then after adding the peak, you have to accept it so that it will get accepted. So how this software is used to plot the graph, deconvolute the graph. Okay, and these are the uh, database where you will get the standard value, standard binding energy of that particular compound. Okay, so that's all from my side. Sir, काही प्रश्न असेल, any questions, please
Yes, sir.
ask, or you can ask. I will share my number and email address also here. You can contact me also. Satish sir.
Thank you, sir. Yes, sir.
Yeah, sir.
Thank you, sir, for your wonderful lecture and presentation. I request participant to, if they have any question, type in the chat box.
Chat box. Okay. What is that? Please show here. See, if you right now you don't have question, you can ask later on, or you don't understand it. There is a two thing. If you don't understand the thing, lecture, or you don't have right now questions. Anyway, you can contact me on my email. I will give my email address also here.
Okay, sir. Okay, sir. As we come to end of today's webinar, it is my privilege to deliver vote of thanks. So on the behalf of Chemistry Department, Mahatma Gandhi Vidya Mandir, Loknete, Venkatrao Hire, Arts, Commerce and Science College, I extend my vote of thanks. Great gratitude to Dr. Govind Umarji sir for sharing such valuable insights. Also, my heartfelt thanks to Principal Sir, HOD Sir, faculty members, research scholars, participants for joining webinar. Thank you, sir.
Thank you, Satyam sir. Thank you, Satish sir. If there are any queries, please let me know. I will more interact. More happy to interact with you all research scholars and
Okay, sir.
yes, sir.
सरजी हॅलो
हाँ बोला सर.
काय नाही शेअरिंग स्टॉप करता का
हो हो.